Welcome to Lecture 7, Moment of a Force, Vector, and Principle of Moments. We'll be looking at a vector operation known as the cross product, and then we'll use the cross product to help calculate the moment of a force when that force is in Cartesian form. And then we'll look at what's known as the principle of moments. In the previous lecture, we learned how to calculate the moment of a force about a point using scalar techniques. Now we're going to develop a more general method of finding the moment of a force about a point that we're going to use in our 3D work. And we're going to make use of a vector operation called the cross product. So let's consider two vectors A and B. And we say that the cross product of A and B yields the vector C. So shown here on the diagram, here's C. And we write that as C equals A cross B. Now note that this is not a multiplication sign in this instance. It's read as cross, not multiplied by. And we should note that the order of the vectors matters when you're crossing two vectors. That is to say that A cross B does not equal B cross A. It actually equals minus B cross A, but the thing to note here is that the order of the vectors matters when you're doing cross products. So C is a vector. This cross product is a vector, so it must have magnitude and direction. So let's look at the magnitude first. The magnitude of C is given by the magnitude of A times the magnitude of B times the sine of theta, which is where theta is the angle in between the two vectors. And knowing what we know about the sine function, you should be able to see that this magnitude is going to be greatest when theta is 90 degrees or the vectors are perpendicular. Let's look at the direction of C. C will be perpendicular to the plane containing A and B, and its direction can be determined by the right-hand rule. So let's go back to our diagram. For crossing A into B, we put our fingers out along in the direction of A so that we can, when we curl them, they go towards B. And when we do that, our thumb will point along the axis along the axis that contains C and in the direction of C. And if we know a unit vector, if we can determine the unit vector in the direction of C, we can write that C, vector C, equals A cross B, which equals the magnitude of that cross product times that unit vector in the direction of C. Before we discuss the cross product of two general vectors that are written in Cartesian form, let's look at cross products involving the Cartesian unit vectors I, J, and K. So with three vectors, we have the possibility of 9 different cross product equations we can write, and we'll look at those three at a time, beginning with these three. And we'll start out by saying that I cross j equals k, and let's see if we can figure out why we can say that. So we learned on the previous slide that the magnitude of the cross product of two vectors is equal to the magnitude of the first, which is 1, the magnitude of any unit vector is 1, times the magnitude of the second, which is 1 again, times the sine of the angle in between the two vectors. So by definition, the angle between any two Cartesian unit vectors is 90 degrees, and the sine of 90 is 1. So the magnitude of I cross j is 1. Now for the direction, we need to use the right-hand rule. So let's look at the figure here on the lower left. So if we're going to cross I into j, we extend our fingers down the x-axis in the direction of I, such that when we curl them, they curl towards the y-axis, or which contains the j unit vector, and then our thumb should be pointing in the positive k direction. Okay, so the result of I cross j is 1k, or just k. J cross k, k cross I are similar. Let's look at the second three. Now we have I cross k equals minus j. Let's see if we can figure out how we got that. So change colors back here first. Okay. So again, we have a magnitude of 1 times a magnitude of 1 times the sine of 90. So the magnitude of the resulting vector is 1. And for the right-hand rule for I cross k, let's go to purple. So for I cross k, I'm going to extend my fingers down along I again, but this time position my hand so I can curl the fingers towards k, and you see that your thumb points in the negative j direction. Okay, so I cross k is equal to 1 times negative j, or just negative j. And k cross j, j cross I are similar. Now, the standard way of remembering this, something that, you know, on a test or whatever, you can just sort of sketch from memory, is this circle here, where I, j, and k are shown on the perimeter of the circle. And how you use this is, if you're going counterclockwise around the circle, for instance, you're crossing I into j, the result will be a positive k. You have to remember that going counterclockwise means you're going to have a positive result. And when you go the other direction, you're going to have a negative result. So let's look at I crossed into k. that will yield j, but now you're going clockwise, so it's negative j. So this is, again, a pretty standard way of remembering the cross products of the Cartesian unit vectors. Okay, the last three are the easy ones because any vector crossed into itself is going to be 0. And the reason for that is because theta, the angle between the two vectors, is 0, and the sign of 0 is 0. So I cross I is 0, j cross j is 0, k cross k is 0. So now we can look at the more general case of a cross product of two vectors written in Cartesian form. So here we have vector A written in Cartesian form, vector B written in Cartesian form. So A cross B can be calculated by taking the first term of A, crossing it into the first term of B, first term crossed into the second term, first term crossed into the third term, second term crossed into the first term, and so on. So you're going to have 9 individual results from that work, and 3 of those are going to be 0, because remember that when you cross any vector with itself, the result is 0. So the I cross I term is going to be 0, the j cross j term is going to be 0, and the k cross k term is going to be 0. So we're going to have 6 terms resulting out of that. And then when we combine like terms, that will yield the following. Oops. And this is the result of the cross product of two vectors written in Cartesian form. Now, in the next slide, we're going to see how to use determinants to do this, which is generally the preferred method. For two general vectors, A and B written in Cartesian form, we can express the cross product in determinant form, where A cross B is expressed by this determinant. The order of the rows matter. In other words, we're always going to put I, j, and k in the first row. And if we're crossing A into B, A needs to show up in the second row, B needs to show up in the third row. If we were crossing B into A, the order of A and B here would be reversed. Now we can expand this determinant, and this may be familiar to you or not, but you do need to learn how to handle these. Either that, or you need to use the formula on the previous the equation on the previous slide. I think this is the preferred way. It's just it lends itself to better organization and structure, I think, when doing these cross products. Okay, so we're going to have, when we expand that determinant, we're going to have an I, a j, and a k term. And to generate the I term, doing determinant math here, we cross out the row that contains I and the column that contains I, and what's left is known as the minor of I. And what we're going to do is we're going to start with the upper left term, multiply it by the term across the diagonal here, come up here and say minus the product of these two terms. So our result is going to be I times the quantity AY times BZ minus AZ times BY. Now, if you go back and look at the previous slide, you'll notice this is exactly what we wrote for the I term on the previous slide. Okay, for the J term is going to have a minus sign in front of it already. That's a given based on the definition of the expansion of a determinant, a 3×3 determinant. And to find the minor of J that we're going to use, we're going to cross out the row that contains J and the column that contains J, and then we're going to do the same multiplication and subtraction. We're going to say A sub x times B sub z minus A sub z times B sub x. And again, if you look at the previous slide, that's exactly what we had for the J term in the on the previous slide. Okay, and then finding the K term is similar here. Armed with all of this math, we can now begin the statics portion of the lecture. We can express the moment of a force F about some point O using this equation, where R is any position vector from the point O to the line of action of F. Let's look at this diagram here. Here's point O. Here's F acting along its line of action. And R can be this position vector or any one of an infinite number of position vectors from O to F. Normally, you're going to pick the position vector. You're going to use a position vector that you can easily write in Cartesian form. In other words, if this were a problem, we probably know the coordinates of the point A and the point O, making it easy to write the Cartesian form of the position vector from O to A. Now, as far as using the right-hand rule to determine the direction of the resulting moment, you need to connect F and R tail to tail. So you would bring R out here for the purpose of using the right-hand rule. And then you would extend your fingers along the direction of R such that you could curl them into F, and you would see that your thumb points this way. Okay. Now notice they're showing D, the perpendicular distance between the line of action of F and O. And in 2D problems, D is usually fairly simple to calculate using trigonometry, geometry. But in the more general case, where it's a 3D problem, D can be very difficult to calculate. So in most of our 3D problems, we're going to use this vector equation to find moments. Okay, let's look into a little more detail with what we mean by any, that R can be any position vector between O and the line of action of F. So it's illustrated here in this diagram. Here's O, here's the line of action of F, and any position vector between O and F can be used in our vector equation. So there's literally an infinite number of position vectors. Again, you're going to pick one that's convenient, or the one that's most convenient to produce a Cartesian form of R. Now, the fact that we can do this is based on the principle of transmissibility, which says that a force F can act anywhere along its line of action and will have the same effect on the body upon which it's acting. So in other words, if F was acting at a specific point on a body and you moved F to another point on the body that's along the line of action of F, then the effect on the body is going to be the same. So in the general 3D case, where we have F creating some moment about a point O, we can express that moment using this equation. Again, where R is any position vector from O to the line of action of F. And we can write this cross product in its determinant form, where R sub x, R sub y, R sub z are the magnitudes of the I, j, and k components of R, and f sub x, f sub y, and f sub z are the I, j, and k components of F. And just reinforce that here with these notes. And it's important, as we discussed earlier, the order of the vectors matters. It's always going to be R cross F, where R needs to be in the second row of the determinant and F needs to be in the third row of the determinant. The last thing we need to talk about is the principle of moments, which can be a very convenient method to use in 2D problems, depending on the problem. And the principle of moments states that the moment of a force about a point is equal to the sum of the moments of the components of the force about that point. So let's see if we can make sense of that looking at this diagram here. So we learned previously that the moment of some force F about point O, using scalar techniques in 2D, is going to equal the magnitude of F times the perpendicular distance D from point O to the line of action of F. And in a lot of problems, in a lot of 2D problems, D is relatively straightforward to find and is the best. And so using F times D is the best way to solve the problem. But in some problems, it may be difficult to find D. And the principle of moments says that instead of calculating F times D, we can take the magnitude of the X component of F. In other words, we take F and break it into its two rectangular components, F sub X and F sub Y. So if we then take the magnitude of the X component of F and multiply it by the perpendicular distance between the line of action of F and O, which is just going to be if the Y distance between O and the line of action of F, and they're just showing it over here, but it's the same distance. Okay. And then in this case, if clockwise moments are positive, this was creating a positive moment about point O. Now the Y component of F is right here, and the perpendicular distance from the line of action of F, not the best line, to O is just the X distance from F to O. And F sub Y tends to create a counterclockwise rotation about O, so we're going to have to put a minus sign there. But it's just the magnitude of the Y component of F times that X distance there. So all we've done here is just take a single force F, break it down into its two components, and then use basically FD for each of those components. But again, this can save you a lot of time in some of the 2D problems.